Okay, let's we'll start. So, so this will be the last lecture that we have. I mean, today is not the 28th, 30th. And we'll basically finish the proof that you know, we have been discussing for a while, which is to go from worst case hardness uh, to the conclusion that Nissan-Wigderson had. So let's just recall Nissan and Wigderson's theorem, which basically said that, suppose someone gave you an explicit function, which was hard for 2 to the delta k size circuits. Okay, for some constant delta. You fix any constant delta that you want, and you're given a language in exponential time that is this hard. And it's like this hard to guess, in the sense that no circuit can get an advantage significantly better than half. That's the setup that we are in. Then we saw that then P must be equal to PP. Okay, so hard to guess was referring to the strongest notion among the 3 that we have written, which is that every circuit basically is going to do a little bit better than random guessing, but not much beyond that. Okay. The second thing, hard to approximation, is like saying that every circuit makes a mistake on some small fraction of places. Okay. And sorry, some chat that is happening here. Anyway. And then the third thing is like hard to compute, which is the worst case hardness, which is that you always just want to say that every circuit of the size bound that we have makes a mistake at least at one place. So those are the 3 setups that we are in. And we are somehow trying to go from the weakest possible assumption and get to the conclusion that came from the strongest possible assumption. So we're basically trying to move from here to here. And what was the rough agenda of what we were following so far, which is basically that we said, okay, let's start with a function f on k bits, which I'm going to think of as a truth table of length 2 power k. Okay, and then we'll apply some code on it, some error correcting code, and convert this truth table, the string of length capital K, to a string of length capital K prime, where K prime is a little larger, and interpret the string as some function. Interpret it as a function on more bits. And the hope is that if this function was hard to compute, this function is hopefully hard to approximate. And what was the rough idea? Where this is exactly where the fact that we were dealing with a locally decodable code was most useful, wherein we wanted to basically say that, look, what do we want to do? We are told that, given a circuit C, we can somehow find, let's say someone tells us that there is a way of approximating F prime. Then we were going to basically run the local decoder on C to get any specific value here that we may have been interested in. So that was roughly how the proof went. And the locality was important to make sure that in order to compute a single bit, you're not like reading the entire string here. You're only querying it at a few places, etc. But so this is roughly what we had. So the rough agenda was, idea was that, if someone told us there is a small circuit C prime that happens to approximate the function well, then the decodability is going to tell you that I can now build a different circuit C that actually gets it correctly with, at all places. Okay. And so the contrapositive of that is that if I know that F is hard to compute, then I know that F prime is hard to approximate. Okay. So that was this is how we went. And the size parameter degrades by the running time that the decoder takes. But it's not it's hopefully, the size parameter here we are dealing with is like 2 to the delta k or something. Whereas a decoder is sort of running in polynomial time. So we didn't, it was like, this running time of the decoder wasn't really hurting us. Okay, good. Now we then said that, Reed-Muller codes have some sort of local decodability property. Actually, I should not have been saying that 1 by 12 locally decodable. I should be saying that it is locally 1 by 12 decodable. Like in the sense that, it's a parameter of the decodability, and locality is just an extra property that you have here. Okay. And what was the decoder basically? So suppose I want the value at this point. And the idea was basically, let's just shoot a random line through that point, read off all the values along that line, that was supposed to be a Reed-Solomon code, which is corrupted at a few places. So we run the appropriate Reed-Solomon decoder and answer according to whatever the Reed-Solomon code word was. So that was the rough idea. And we just had to basically tell ourselves that, if the number of errors is like, I don't know, 1/12 of this or something, when you shoot a random line, you don't expect to hit this error like significantly more than 1/12. Like you sort of say that, even on a random line, you still expect about, I don't know, maybe not 1/12, maybe, but certainly like at most 1/3 of it are errors or something. And we set up the rest of it accordingly. This is what we did. But this was, of course, read Muller codes is like over a large field. It's not over a small field, but this is usually not a problem again, because we can always concatenate with a code that is good. So we basically said that if you concatenate it with a Hadamard code, then you lose a little bit on the decodability, but basically you're still going to get decodability, and now you have a truly binary code. Okay. And so therefore, the upshot of all of that was that, given a function that was worst case hard, we managed to construct a function that is a little hard. It's at least hard to approximate. Okay, so this is what we had done last time. Okay, so now the goal is to somehow improve 1/48 right now. Okay, so what I want to do is I want to go from something that is worst case hard to something that is actually whatever, half minus epsilon hard to approximate. I want to improve this 1/48 to something like, I don't know, 49.99%. Okay. And the reason I'm doing this is because half minus epsilon hard to approximate is the same thing as it is epsilon hard to guess. Okay. And that's where we are trying to get to. And like something that I briefly mentioned last time is that intuitively, this is again a question of you're asking for a code, you're asking for a binary code that is delta decodable, where this is replaced, this 1/48 is replaced by something like half minus epsilon. But asking for a half minus epsilon locally decodable code is sort of impossible, because every binary code that has at least 3 strings in it or something, the distance will be at most half. Okay, which basically means that if you want to uniquely decode, you can't tolerate more than a quarter of the errors. But now you are somehow saying that I should be willing to tolerate something like half minus epsilon errors. That seems a bit too much. It's like well past the unique decoding radius. So we need to therefore say that, okay, we can no longer do unique decoding. We have to move on to list decoding. But somehow the key in all of what we were doing right now was basically there was a notion of locality that worked in our favor. So we need a concept of what is called locally, like a local list decoding algorithm. Okay. And what's the rough idea? So let's say G is our received word. Okay. So there is some received word that we have. And for the sort of error that we are willing to handle, there may be several code words close to G. There need not be a single one. There could be multiple now. But on the other hand, what are you interested in? You are basically interested in, I want to know what is the value of, I don't know, the xth coordinate. Maybe I care about what is the correct, I'm interested in, I want to correct a specific x here. And I'm interested in what is the right value supposed to be there. Now, it depends on which code word you are then talking about. Maybe if it is this code word, this is the right value. If this is a code word, then this is the right value, etc., etc. So you need some way in which, what does it mean for an algorithm to tell you, saying that, okay, these are the possible values. Okay. And a natural candidate is going to be that, the decoding algorithm has access to G. It is given input X, and it outputs this list, like all possible values that it can see on the xth coordinate. The problem with that is that typically you are going to be dealing with a regime where the list size you are talking about is much larger than the alphabet size. So it's very likely that, every single symbol of the alphabet sort of shows up in one of those code words. Well, in that case, if the decoder algorithm is just going to output sigma, it's not helpful at all. You're not giving any useful information. Okay, so you need to come up with a way in which the decoder is truly doing something non-trivial. It is answering honestly according to some code words rather than just telling you this list of symbols. And in order to do this is where this concept of like a, whatever, let me call it a local delta, this is a local delta list decoder. Okay, that is the errors that you're willing to tolerate is like delta. Or I shouldn't say error, like the distance that you're, I mean, the Hamming distance is like delta. That's how close you are. Okay. And so this decoder actually consists of two algorithms. So the decoder is going to run in two phases. There's phase one and phase two. I tend to think of calling the first phase as the advice phase, and the second phase actually as the decoding. Okay. So let me briefly describe what is going to happen. Okay. I'll first give like a whatever broad view of what is happening, and then we'll look at the formal details. So the first step is going to be the following. The decoder actually is going to have access to just G. It's not going to be told X. I mean, for the advice phase. And then the decoder at that point will say, hey, look, based on your G, I feel there are code words, there are these R code words that are potentially close to you. Now, I don't know which one you want, but I will give you a label for each of those code words. I will call this code word A1, this code word A2, and this code word AR. That's what basically decoder 1 just does the following. It looks at G and outputs this list A1, A2 to AR. I mean, those don't particularly have any meaning. It's just some way of the decoder indexing which code word you're talking about. That's it. Now to decoder 2, to that you give it a point X along with an AI. And then you say in the AIth code word, what was the value of X? So the first phase is what is used to disambiguate between the various potential code words. So the first phase is going to tell you, look, this is a list of potential code words that I have. So the next phase, you fix one of those things in the list and then ask based on that. Okay. So let me now go over what the thing is. So basically, like I mentioned last time, I mean, like I just mentioned, so decoder 1, the advice phase, it just looks at the received word and just returns some list A1 through AR. I mean, you can think of A1 through AR as strings, as numbers, whatever. It doesn't have any meaning. It's just a way of tying the hands down to one specific code word. That's all. Okay. The second one is more like the local decoding property, which is it takes a specific coordinate that you care about along with one of the things that was there in this list. And intuitively, you are asking in the code word corresponding to AI in your list, what was the correct value at X? Okay. And I'm going to let this algorithm fail, in some, I mean, maybe, it was being a little liberal about what this list is, but after the decoding phase, it realizes, oh, this code word doesn't even exist. So maybe it fails. Okay. But the important thing is, what is the guarantee? What do you want this decoder to actually achieve? Okay. Now, what I want is the following, which is, suppose you have a specific code word that you're interested in. There is some code word that is within the required distance of the received word. Then I want the following to happen. Okay. I want to say that with high probability over the first step, I mean, the decoder 1 is going to be some randomized process that generates A1 through AR. I want to say that one of these AIs that the first step generated actually corresponds to the code word F. That is, I want now if I vary X, I keep AI as fixed, I keep varying X, it must actually equals F of X for all those values of X. Okay, is the definition clear? It's a tricky definition, but it's like it captures exactly what you want it to capture. You're sort of saying, okay, fine. You say you have 10 code words that you can answer using. Then I'm going to say, okay, fine. Let's fix the 7th code word. According to the 7th code word, I want the value at this point. Can you tell me the value there? And I want the property that if there was an F that was actually close to my G, that F should show up in this list somewhere. Like one of these AI should correspond to that F. Okay. And this is called a local list decoding algorithm. Okay. And it removes this thing of, you can't just output sigma now. Because once I fix an AI, you have to answer all other coordinates in a systematic fashion. I mean, you can't keep changing the code word depending on the coordinate. It's sort of the AI lets you tie your hands down to one code word and then focus on that and answer according to all the things. Okay, cool. So now that that is there, again, the running time I'm going to say is again some T decoding. This is going to be polynomial in the parameters involved, which automatically means that R is going to be at most T decoding. And it also means that the number of queries that this decoder will make will also be within that and so on. Same, so that we don't have to deal with multiple parameters going forward. Okay. Okay, good. So now the first thing that I want to claim is that this local list decodable codes are also enough for the sort of things that we were doing with locally decodable codes. So previously we said that if you have a good locally decodable code, you can use that to do this hardness amplification. And we're going to say that the same is true even for locally decodable codes. And in fact, here, the fact that you're dealing with circuits is going to be a lot more crucial. Like you're not dealing with algorithms, you're dealing with circuits. Okay. But the proof is almost identical. So what are you going to do? You're basically going to say, well, suppose someone told us that, there is some C prime that apparently gets F prime right with probability half minus, like 1 minus delta. Now, what are you going to do? You're going to run the local decoder with C prime as input. Now, F prime is actually one of the strings that is close to C prime. Which means, based on the whatever choice of randomness here and so on, there are several choices of initial randomness. And there is a specific AI that once you fix that AI, you are now truly talking about F prime here. Right? It's just that I don't know what the AI is, and I don't know what randomness I need to fix. But I don't need to know. I mean, all I need to basically say is that there exists some randomness that works, and there exists some AI that works. So we will hardwire that into the circuit. Because all we are trying to say is that there exists a circuit C that computes F everywhere. And well, you take the circuit C prime, you run the decoder, but you specify which random, whatever initial choice works and what specific AI it needs to work with. And that's it. So, and obviously the same guarantee sort of work that you will have a degradation of something like T deck or something. Oh, sorry, this should have been, oh no, this is fine. That is, if something is hard to approximate for a smaller size, I mean, the size now increases by a factor of T deck. I mean, if you have a size S prime circuit that computes this, then to finally get a circuit that computes this exactly, you will have to run something on top of it. Okay. So is this okay so far? Okay, great. Okay, so now that we have this, we come to the main, the last part that is left, which is, this was the key contribution of Madhusudan, Luca Travesan, and Salil Badan in this paper, to basically say that, no, the Reed-Muller codes we were using previously, they actually are a locally list decodable code as well. Like we don't just have local decodability, we actually have local list decodability. And this will allow us to basically say that, in one shot, you go from worst case to hard to guess. Okay. And the algorithm is beautiful to describe, and the analysis is surprisingly not very complicated. Okay. So here is let's just make sure that we are on the right page. So we are talking about Reed-Muller codes, which is like you're working on M variables, but degree D. Okay. And let's say you're working over a field FQ. Okay. So every string in the Reed-Muller code, the alphabet is sigma is FQ. Okay. And the block length is Q power N, because the block length, every coordinate corresponds to a point in the ambient space. And the ambient space is FQ power N. Okay. So the block length is Q power N. So they're all strings in FQ power Q power N. All right. And what is the setup that we have? Now, let's say G is potential received word. Okay. And since in most list decoding setups, we will work with agreement because we are going to really be in the 1 minus delta sort of regime. Okay. So I'm going to define something called list epsilon of G, which is what are all read-Muller code words that agree with my G on some epsilon fraction of places. Okay. So this is like I'm tolerating an error of 1 minus epsilon. I'm basically saying I'm only looking for agreement, which is epsilon. So I can handle close to 1 minus epsilon errors. You might be asking, why do we care about 1 minus epsilon? Didn't we just need half minus epsilon? But at some point, you will have to do a code concatenation with the Hadamard code. So there, that 1 minus epsilon will now become half minus epsilon eventually. But for now, let's just play with this. Okay. And we are going to be working with epsilon that sort of looks like, this should remind you of what we were doing when we were looking at Reed-Solomon codes and Johnson bound and stuff. So the epsilon is going to be like roughly some big constant times square root d over q. Like if you really, it will so turn out that the size of this list, okay, this will also be something like square root of q over d, but there'll be some other constant c prime that shows it. That is, if you jack up this constant starts going down. Like if you ask for more agreement, the list size becomes smaller and smaller. Okay, we did a specific instantiation of this when we did a proof of Johnson bound and stuff like that. But we'll be working with some C which is large, let's say 1,000 or something. And what I want is a local list decoder to get this entire list. I want some algorithm which gives me a way of accessing every function f in this list. Okay, so let's just define what the two things do. Okay, so the first step is going to be the following. I'm first going to pick a uniformly random point y. Okay, and this is my list I'm going to output. I'm going to output q things in my list, which is like y comma a for every a in fq. Okay, intuitively tell yourself that this is like saying, this is a list of polynomials and I'm saying that at the point y, my polynomial takes value a. That is how I'm trying to disambiguate different polynomials. Okay, right now this list size is much larger than what I need. So some of them I might return bottom later on. But this is my list size. I want to make sure that every legitimate polynomial is covered here. Okay, so this is the first step. I mean, this is not particularly insightful, but the fun part is what happens in the second thing. Okay, now you fixed a particular advice string, y comma a. And now you care about what is the correct value at x. Okay, so what you do is the following. You take the line joining y and x. So, okay, if x was equal to y, then just return a. Okay, that's what you're going to return. But if x is not equal to y, there is this line joining y and x. And that's given by this equation, whatever, ty plus 1 minus t times x. So that when I set t equal to 0, I get x. When I set t equal to 1, I get y. Okay. So you take this line, and now you query all the points on this line. Okay. And you query all the points on this line, and now you run the list decoding algorithm for Reed-Solomon codes, where you're looking for all code words that have agreement at least epsilon by 2 on this line. We've already seen a list decoding algorithm for Reed-Solomon codes. So that's what you run at this point. But now you will get a list of things. You'll get a bunch of polynomials f1 through fr. Okay, now you need to know, what am I supposed to answer? Like, do I give f1 of 0? Do I give f2 of 0? Which am I supposed to give? And that's where the advice point is going to show up. And you basically ask, among this list of polynomials, is there a unique polynomial that takes value a at 1? That is there a unique polynomial that is assigning the value a at the point y? Okay. If there is a unique polynomial, then you are able to disambiguate between this list. Like this list of polynomials, only one of those polynomials take value A at the point Y. So you answer according to that polynomial. But if it so happens that none of the polynomials take value A at 1, or two or more of the polynomials take A at 1, I'm just going to give up and say, no, no, no. Now I am, this is not going, I don't know what the answer is. Yeah.
Again, what was in the definition of local list decodability? What did we want the
We
decoder bar
wanted
to
to
do? What
make
was
sure that for every code word that is actually close to you,
uh,
okay, there must be one of these I's, one of these AIs that was returned in the first phase, that must actually correspond to f of x everywhere.
that must correspond to perfect.
So some of these A's could just return bottom. Like, some of the coordinates, it could just completely fail. But what you want is one of those A's must actually result in like all the things being recovered.
Hmm. Hmm.
Okay. So here that's what is going to happen. So we have fixed a particular y and a. And at a given point x, we are going to try and see if we can figure out what the value at x is.
Hmm.
Okay. And the way we are going to figure that out is you take this line joining x and y, do Reed-Solomon decoding on this line,
On that.
and hope that the y comma a disambiguates between the polynomials that you currently have.
Hmm.
If it does disambiguate between these polynomials, then you answer according to the one thing you managed to filter out. But if you're not able to disambiguate, or maybe you threw away all the polynomials, like none of the polynomials took value a at 1, then you return bottom.
Hmm.
Okay. So this is going to be the decoder. So the theorem that we are going to prove is the following. That we're basically going to say, let's fix an actual Reed-Solomon code word that happens to agree with my given vector g on some epsilon fraction of places, where epsilon is like c times square root d over q, c is some large constant. Then I want to say for at least half as many points initially chosen, okay, had I chosen the advice value to be equal to f of a, I would have actually recovered this for all values of x. Like if I happen to choose the right value at the point y, then for all points x, this is what will happen. But technically speaking, actually, I'm going to cheat a little bit, but it's not really cheating. That I won't be proving this statement. I will instead prove the statement that this happens for 99.99% of x's. That this is not going to happen for all x, but it's going to happen for almost all x. So can someone tell me, how do I go from a statement of this sort to a 100% statement now? I mean, this decoder is not going to work because this decoder is only going to guarantee this much. But I want to do something on top of it to actually get a decoder that gets it right everywhere.
You stack another code on top
Yeah,
of
we
it.
already have seen that, if you have agreement, which is like, if you have error at most, I think 1 by 12, then we knew how to do local decoding at that point. 99.9% is already within that thing. So now think of this as your new received word that is within like 1 by 12 of the actual code word, and run the local decoder we did last time. So it therefore suffices to show that for most values of x, this happens. Because as long as I go past the unique decoding radius, I can run the local decoder. I mean, like, okay, so that's, so what we are going to show is that this happens for almost all values of x. Okay, is it okay so far? Okay, good. So, good. So now what we are going to get a sense of is like, I want to know if I pick a y at random, Okay, so at the moment, let's fix the following. So we have fixed the received word G. That's the received word we got. And we have a specific code word that we're interested in. This is actually in the RM, the Reed-Muller code word, code space. And we know that, what I shouldn't say delta, we know that the agreement between F and G, this is at least epsilon. So that's the setup that we are in. And I want to know if I pick a Y at random, uh, like what are the chances that I actually happen to decode correctly to f of x? And I want to say that for a lot of the such x's and so on, this must happen. So here is the claim I'm going to make. Okay, so we're going to try and think of so the following. Here is what is happening. So there is a y that is sort of randomly chosen. Okay, and there is an x that is also going to be randomly chosen, because I'm trying to figure out what fraction of x's am I going to get it right. Okay, which means there's a specific line LXY that passes through x and y. So let's think of this distribution that we are dealing with. Okay, the distribution that we are working with is I pick a y at random, I pick an x at random, and there is this line connecting x and y. Okay, but if I look at the marginal of just what happens on the line, that line is also a uniformly chosen line in their entire space. Okay, so we are going to interpret this distribution in a slightly different perspective and argue something about what happens with respect to the line and with respect to the choice of it. So for example, I'm now going to think of it the following way. I'm going to think of it as like, I first pick a line at random, and then I pick a uniformly random point y on that line. Okay, and x is going to be some other uniformly random point on this line. These two distributions are the same. Okay, it's just that sometimes it will be convenient to take the following perspective. So let's do the following. So let's again define the set of disagreements. What do I call it? Let me call it S. So the set X is the set of all, okay, I've already used X and Y. Let me call the set of all Z in FQ to the M such that f of Z is not equal to G of Z. Okay. So this is the set of all disagreements between F and G. Actually, rather than disagreements, let me make it agreements only, because that way I can sort of say the size of S is at least epsilon times Q power n. That's the guarantee that's given to me. Okay. So the first step I want to ask is the following. So what is the probability that if I pick a line uniformly at random, okay, what is the chance that if I look at L intersect S? So firstly, what is the expected value of L intersect X? What will that be? Like what fraction of the line will actually pass through this set S if I choose L uniformly at random? So because the line is uniformly at random, it's basically going to, every point on the line is in fact a uniformly random point, right? So if you just look at the expectation of what L intersect and S is going to be, it's basically going to be the density of S. If S had a density of epsilon in the entire ambient space, if you choose a random line, you expect to hit like an epsilon fraction of it. Okay. So the expectation is again going to be something like epsilon times Q. But I am actually interested in some form of concentration. I want to know what is the chance that this L doesn't hit anything of this agreement points. That is specifically, I want to say, what is the chance that this is at most, say, epsilon by 2? Okay, so that's the first thing I want to calculate. I'm soon going to show that this happens with probability at most some 0.001 or something. Okay, so that's the first step I'm going to say. Okay. So this is something that we have to prove. The second thing that we have to prove is the following. So let's fix a line L that does not satisfy something like this. That is, it's a line, it's one of those typical lines in the sense that it passes through at least epsilon by 2 of the set S. Okay, so fix a good line. Okay. Okay, and if I fix a good line, now notice that on this line, I am agreeing with the F's restriction on this line with at least epsilon by 2. Because I'm saying epsilon by 2 of the points I picked up. So which means I have agreement with, so which implies that agreement with F restricted on L is at least some epsilon by 2. Okay. And now, but on the other hand, let's say that, let F1, F2, blah, 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 Fr be all univariate polynomials that have at least epsilon by 2 agreement on this line. Okay. So on this line, if I look at all polynomials that have agreement epsilon by 2, I don't know, maybe there are R of these polynomials. Okay. Now I want to know what is the chance that if I pick a Y uniformly at random on this line, okay, F1, blah, 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 till Fr take distinct values at Y. Okay, it could be the case that some of these points, F1 and F2 agree on. Some of these points, F3 and F4 agree on, etc., etc. Okay, and I'm going to say that this is going to happen with probability 1 minus 0.0001. Again. Okay, so these are two claims that we will soon make. But let's see why, if we make these two claims, we are actually done. Okay, let's see why that is the case. When will I be able to correctly decode at a uniformly random point X? Well, if I'm choosing a uniformly random point X, since I initially picked up a random point Y, the line under consideration is this line joining X and Y, which is now a uniformly random point. Okay, we are currently saying that all but a point, not one fraction of lines are good with respect to the first inequality. Like they sample the good points well. And the second thing is saying the point Y that I chose on this line was able to correctly disambiguate between all of them. So in that situation, I know for a fact that F restricted to L is one of the lines on this list. And therefore, I will be able to correctly disambiguate to F restricted to L only. And I will therefore output the right value at X. So basically, like if the point Y is chosen correctly, we are basically saying that, all but a point, not one fraction of lines around it are going to be good. And on those lines, I'm going to correctly answer all the values on those lines. It's just that there is a small fraction of lines at which I might fail. So those are the points X on which I potentially may be returning bottom or something. Is this clear so far? So you are basically going to just argue that these two things hold. If these two hold, we are done, that this probability and this probability holds. And that will tell us that the decoder that we wrote above is actually a local disk decoder. Okay, actually, let's do the second part because the second part is easier. Okay, now let's just ask ourselves that, so we picked a line L at random. So this is some line, and there are polys F1 blah 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 to Fr that have at least epsilon by 2 agreement with G restricted to it.
So this is a polynomial in that variable T.
Yeah, in the okay, yeah, they're all polynomials in T, and this also I'm thinking of as a polynomial in T. Okay, as univariate polynomials, they have epsilon by 2 agreement. Now the point y that I'm choosing is some uniformly random point here. And I want to know what is the chance that, what is the probability where I choose this y uniformly at random from L, that there exists some I and j such that, in fact, I don't need to say that they take distinct values. I'm going to say that, uh, uh, let me replace this to say, no poly other than f restricted to L. F restricted to L is certainly one of the polynomials here. I just want to make sure that that value is not taken by anybody else. Okay, takes the same value at y. Okay, so this is what we actually need because we are trying to figure out, we disambiguate that one thing from all the other polynomials. So here I'm asking, so let's without loss of generality assume that f1 is the polynomial that we care about. F1 is actually f restricted to L. So the probability that there exists I not equal to 1 such that fi at the point 1 actually equals f restricted to L at the point 1. Okay, or in other words, rather than saying fi is, I mean, since we are talking about univariate polynomials, there's a specific univariate polynomial f1 we care about. Okay, and we are basically asking what is the probability that fi at y is equal to f1 at y. I mean, it's why calling it 1 or y or something doesn't, I mean, we are talking about that line. Okay, and now let's ask ourselves the following. If I take a polynomial other than f1, how many points of agreement can it possibly have? We are talking about 2 degree D polynomials. There can be at most D agreement. Okay, so this, a stupid bound that you have is this is at most R times D over Q. Okay, because with polynomial f2, there are at most D agreements. With f3, there is at most D agreements, blah, 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 till, I mean, there are R such polynomials that are going to be D. And what is R going to be? R is basically going to be square root of Q over D. Okay, by some large constant C prime that is here, times D over Q. Okay, so, so this is basically going to, I mean, you can drive this down as much as you want. So because this is essentially going to be, this is like order of square root of D over Q. And so, I mean, like if you set Q to be large enough constant compared to D, you make sure that this is like 0.0001. Is this okay so far? Okay, so this part is like, there's nothing fancy that is going on. It's just saying that once you know that you're on a line, which is a good line, in the sense that the correct polynomial you care about is one of the polynomials in this line. Okay, then there are lots of points on this line which all are going to disambiguate successfully. So the chance that you ended up picking a point y that was not something that was disambiguating, the chance of that is like really, really small. Okay, so this is part 2. Part 1 is where we need a little bit of setup. So therefore, so what do we have to show? We have to show that the probability that if I pick a line uniformly at random, that somehow this L's intersection with S is smaller than epsilon by 2 times Q. I want to say this chance is very small. Okay, so we know that the expected value of L intersection S, when L is picked uniformly at random, this is actually going to be the size of S divided by Q parent. It's actually going to be the right density. But so therefore we know that the expected value is like at least epsilon. And we're asking what is the chance that your value is like away from this expectation by a factor of 2 or something. So now you can do one thing. You can apply Markov's inequality. But the point is, if you apply Markov's inequality, you will only get this is like at most half, which is not going to be good enough. Okay. Now it feels like I want to apply Chernoff bound. But the problem here is like, Chernoff bound I can apply only if the random variables are like independent. Right. So let's sort of say that, let's give it a name. Let's say Wi is the indicator variable that the ith point on the line is in S. Okay, so the line has q points and you order them in some way. Like, for example, if the line is given by an equation, like set t equal to 0, t equal to 1, this is t equal to I. Okay, so what I know is that the probability that Wi is equal to 1, this is actually equal to the size of S divided by q bar. Because if I fix one of those i's, it's like a uniformly random point in space. Okay, but the problem is if I know what W1 and W2 are, notice that you already know W3, W4, etc., etc., because that completely determines what the line is. So it's like once you know 2 points on this line, you know the equation of the line, and therefore you know all the other points. So they are definitely not independent. Okay, but they are not independent as knowing 2 points on the line uniquely determines all the points. Okay, so they're not independent. We can't quite apply Chernoff. Okay, but notice that I'm also saying that they're not even 3-wise independent, because knowing 2 things, I know everything else. But fortunately, they are pairwise independent. I mean, basically because even if I ask, what is the chance that the first point on the line is a specific x1 and the second point on the line is a specific x2? Well, this is the same no matter which x1 and x2 you choose. Because once you choose x1 and x2, there is a unique line that passes through them. Okay. So therefore, I mean, the chance of this happening is exactly 1 by q power m the whole square. Okay. So therefore, this is a property that is used a lot in many of these things, which is that if you pick a line at random, you have q pairwise independent samples. It's not like you have independent samples. But if you pick a line at random and just use that for your empirical average, you are really doing an empirical average using pairwise independent samples. Okay, and therefore, we can't apply Chernoff bound to get a suitable bound here, but we can apply Chebyshev inequality. Okay, so therefore, by Chebyshev, okay, the probability that L intersect S is at most epsilon by 2 times Q. This is at most 1 over something like epsilon squared times Q. Maybe there is an epsilon by 2 the whole square times Q or something. Okay, Chebyshev inequality will tell us that, this is what you are deviating by epsilon by 2Q from the expectation. So it's going to be 1 over epsilon by 2 the whole square times Q. Okay, so and now let's figure out what was epsilon set as. Now epsilon was set as something like, what was this? So this was at most 1 over some c square root d by q, but now that is getting squared times q. Okay, so if I remove this, so this is going to basically be d by q. There's no squared. The c has become c squared now. Okay, which is like 1 by c squared d or something. I have a feeling I'm somehow maybe. Okay, so this is what you end up with, and so therefore this is something you can drive to whatever 0.0001. You set your c to be large enough, and then this is as small as. Okay, so that basically tells us that these two claims that we were making, that like a randomly chosen line is going to sample the good points with very, very high probability. Like there's a tiny fraction of lines which may be very off in sampling, but otherwise, barring a small fraction of lines, you will be picking up the right fraction of the agreement points. Once you pick up a right fraction of agreement points, that on this line, when you run the Reed-Solomon code word, f restricted to L is one of those polynomials. And now, since if you imagine now picking y at random on that line, the chance that you picked up a y that did not disambiguate is actually very small. Because two polynomials cannot agree too often, and I know that the list size is not very large. Okay, so putting them together, this is going to say that, had I picked up this point y uniformly at random, there must be at least a good fraction of points such that for at least 0.0001 of the x's, I get the right value. The bad x's are those x's that are lying on these bad lines. Okay, once you fix a y, there are a small fraction of bad lines. X's on those lines, I might be doing badly. But every other x, you are actually able to correctly compute the value of it. So this tells us that the second decoder is going to get it right on a substantially large fraction of x's. But we already know that once we go past we have an agreement, like the error is like smaller than 1 by 12. We can then run the local decoder that we spoke about last time. So let me just say, so this completes this theorem. Therefore, dec2 plus local decoder from last time computes f everywhere. Okay, so therefore, Reed-Muller codes are locally 1 minus epsilon decodable, list decodable. Okay, so we're almost done, except that we now have a query code. We don't have a binary code anymore. Okay, but fortunately, very similar to what we mentioned last time is going to work. So something that we noticed last time was that the Hadamard code is whatever. So what it is like epsilon comma. So I should actually be writing half minus epsilon comma 1 over epsilon squared list decodable. We are not talking about efficiently or anything. Okay. So Hadamard code has distance half. So last time we did the local decodability, which was, where it was, we are looking at quarter minus epsilon. But if you recall what we were doing with respect to some Fourier 101 and stuff like that, that time we mentioned that this is actually a code where the list size is actually small, except that this code is of massive, the rate is terrible. Okay, but we this is the same thing as saying that f hat of s this was at least epsilon. And we said that Parseval's inequality says there can't be too many of these Fourier coefficients that are large, because the sum of the squares must equal 1. And you can have at most 1 over epsilon squared of them, therefore. Okay, so a corollary, again, this is using concatenation, which is that Reed-Muller codes concatenated with Hadamard codes is what you end up getting is like you get 1 minus epsilon that comes from, this is the Reed-Muller list decoding radius, times you'll have to adjust for this Hadamard thing. So this will become a 1 minus epsilon times half minus delta. I mean, you set Hadamard where you set this as delta. Okay, comma something list decodable. In fact, this is like locally list decodable. So I'm hoping to put up a problem set or something. One of the things that's going to happen is that if you know that this code is locally list decodable, and you know that this code is list decodable, then concatenation you'll be able to decode up till error, which is like the product of those two. And the algorithm is very similar. You basically decode each of the inner code words, but each of them you will have a list now, but randomly choose one of the elements in the list and then work with that in the next step or something. So, I mean, I'm rushing here because there's no point doing that. I mean, I think that's clearly an exercise question that I will give. But what this will eventually tell us is that this is locally 1 half minus epsilon list decoder. Okay, so it's not like we're even changing the code. The code is exactly the same as we discussed last time. But last time we were using the local unique decodability property to get from worst case hardness to some average case hardness. But this time what we are saying is that no, the same code that you were looking at actually has the local list decodability property. So instead of that, had you just done the local list decoding algorithm, you go directly from worst case hardness to hard to guess functions. So putting them all together, your final theorem, which is the theorem of Impagliazzo-Wigderson. That basically says unless E is a subset of size 2 to the delta n for all delta greater than 0, P must be equal to BPP. So this is like saying if there is some constant delta such that E is not in size 2 to the delta n, that is, there are functions in E which cannot be computed by circuits of size 2 to the delta n, then we showed that P was equal to BPP. So the only way that will not happen is if some crazy situation that every language that is computable in exponential time apparently has a circuit of size 2 to the delta n for every delta greater than 0. Like, unless a crazy thing like that happens, you should be expecting P equals B. And it's because of statements like this that generally the community believes that P equals BPP, because this looks like an outrageous situation. Like, why would you think something like this should happen? Why is it the case that circuits are substantially more powerful than algorithms? Okay, so since we believe that that should not be the case, it's telling us that unless something crazy like that happens, we must have that P equals. So yeah, so this is what I wanted to prove, and so the proof described here is actually the proof by Madhusudan, Luca Travesan, and Salmadan, which is like a one-shot thing directly from worst case to average case. And the key insight in this was the introduction of the notion of local list decodability. And I mean, like whenever you deal with Reed-Muller codes, etc., basically what you do is you restrict to a line or you restrict to a subspace. do something small on that subspace and use that to say something globally. So this philosophy is something that shows up a lot in these sort of questions. And here was yet another example where you could just restrict to a line, do your Reed-Solomon decoding, and just disambiguate based on a random point here. It's just that the random point is chosen beforehand. You first fix the random point and say, I'm going to use this to disambiguate, and every other point, you basically pass a random line. You look at the unique line through X and Y, do Reed-Solomon decoding on this line, and disambiguate using that point. So it's a very simple algorithm. It wasn't even that hard to analyze either. Yeah, and it's a beautiful. Okay, so that's all I want. I was hoping to have one more lecture, but I think now I probably won't. So what I do plan to add one problem set, hopefully today or tomorrow. The grades for the course, etc., need to be submitted by, I think, December 15th. But I was planning to submit it by December 13th or something, because after that I might likely get very busy. In fact, Madhusudan is going to be visiting the department, so I might likely be quite busy after that. So whatever this problem set is and all the previous problem sets, in case you want to try out any of the questions and submit those and so on, just make sure that you submit it by, let's say, December 10th, so that I can submit my grades by 13th, including everything. Okay, cool. So let's stop, and thanks a lot for participating in this course. And